Hi guys, welcome back to Nunley Math. I'm Aaron Nunley. Thank you for joining me here today for writing and solving algebraic equations. Now we've spent the last couple of videos talking about different patterns that can be represented algebraically. We talked about some fun activities involving magic, some fun activities involving calendars, and then we talked about very specific types of problems that tend to pop up in math class. For example, consecutive integer problems, consecutive evens, consecutive odds, and then quite a few geometry problems. What we're going to do today is we're going to take this in a slightly different direction where we're going to be dealing with more what you would consider a traditional word problem. And it's going to look something like this: getting swole. Mr. Nunley and Brennan, that's my son, are working on getting swole. I think that means big and strong. Part of their plan is to put in 45 minutes of exercise each day. If they can do that, how many days will they have to work out in order to reach 1,000 minutes of exercise? So in my class, we talk a lot about taking our time when we're reading word problems. And we discuss the fact that a lot of times people have trouble with word problems, not so much because the math is difficult, but because they're reading it too quickly. When we read in math class, we're reading for very specific pieces of information. For example, when I read this problem, it says, Mr. Nunley and Brennan are working on getting swole. This is a very interesting statement for us in terms of the story, especially since we have the picture to go along with it, but it really has no mathematical meaning. So I'm going to just ignore this for just a minute. And then I'm going to hop down here. I'm going to read part of their plan is to put in 45 minutes of exercise every day. There's a lot of really good and important information in this sentence. First of all, you have this number 45 minutes. That's telling me how long we're going to be exercising. But then there's this word each day, or this phrase each day. And the phrase each day has a very specific meaning for us in math. Because if I work out 45 minutes one day, I would just represent that as the number 45. But if I do it each day, the number of minutes that I exercise changes depending on how many days I've worked out. So after one day it would be 45 minutes, 2 days would be 90 minutes, 3 days would be 135 minutes, and so on and so forth. So this is going to be repeatedly done, or I'm going to be having 45 minutes repeatedly. And hopefully you remember from elementary school that anytime you're adding repeatedly, you're going to be doing some kind of multiplication. Let's hold on to that for just a second. Lastly, you'll notice there's a question. I know because there's a question mark at the end. It says, if they can do that, how many days will they have to work out in order to reach 1,000 minutes of exercise? Notice this number 1,000 minutes. We've got a total amount of time that we want to work out. But there's something else I want to point out. Do you see this phrase right here? How many days? How many days? For us in algebra, that particular phrase is very useful for us because that's going to be the question. The question is, what amount of time measured in days will we need to spend doing exercise? So D is going to be my variable. You see, the question always gives you your variable or unknown. Since the question is how many days will I need to exercise, my variable D is going to represent that. Whenever we do word problems, it's important for you to make sure that your variable or unknown value has some kind of a meaning, and we always want to write that out as we're going. The second thing we're going to do is we're going to write our equation. And the equation comes from the pattern that's given to us. Now, the pattern will be either stated explicitly, meaning do this, do this, do this, do this, or there will be some kind of a pattern that they expect us to recognize when we read this. For example, we talked about this 45 minutes of exercise each day, or this repeated 45, which means it's going to be 45 minutes times the number of days. In other words, how much is my workout growing, or how is my rate changing as time passes? And if I can keep track of that, that will tell me how much work I accomplish. This is a very, very common, very, very useful pattern for you to know. Anytime you have something that's happening over and over repeatedly, as time passes. We call that our rate. In this case, my rate is 45 minutes every day. The amount of time that passes is being measured in days. So if I take my rate, how fast I'm working, multiply it by how many times I work that rate, or how many days that passes, that will tell me how much work I've actually accomplished. So in the case of this problem, I'm working 45 minutes a day, every day for some unknown number of days of exercise, and that's going to give me my total amount of exercise. This thing that's happening repeatedly gets multiplied by the number of times it happens. Or, in the case of this specific problem, 45 minutes a day times d days, remember that's our unknown value, has to equal, well, let's see, how much total exercise do we want to reach? 1,000 minutes. There is our algebraic equation. Now, remember from our last unit that we can rearrange this equation to look a lot of different ways, and that's fine, but this is probably the most literal translation of what this problem says to us. Good news is that setting up the equation is the hard part. Solving the equation should be easy for you at this point because we have 45 times d, and we know that we can solve it using the property of equality. Divide both sides by 45, and we're left with just d equals 22.2 days. And then we want to make sure once we finish, we answer the question. They will be finished working out sometime during the 23rd day. Now, there's always a question as to whether to round this off or not. In this case, I prefer to think of it as I'm not actually working a tenth of a day, a tenth of a day, a tenth. I'm not growing at a steady rate. Sometime during that 23rd day, I'll do that 45 minutes, but I will definitely not be done on day 22. That's why I made this the 23rd day. Now, a couple things I want to point out. You'll notice over here on the left, we're defining a variable, we're writing an equation, we're solving an equation, and we're answering the question. In my class, I would require my students to do all four of these things in order to get credit for the problem. Now, it is not necessarily necessary that you write out your pattern in words. This right here, this equation, is the pattern, but since this is our notes and you're going to want to refer back to them, I'm putting this down for you. This would not appear on the homework. You would write what's here in red, d equals number of days of exercise. You would write this row right here, which is your equation. You would show your work to solve, and then you would give your answer at the end. Got the idea? Let's take a look at another one. Mr. Nunley and Brennan are trying to read 450 books in a year. They have already read 200 books and have 35 weeks left. How many books do they need to read each week in order to reach their goal? Remember, we have 4 steps we have to walk through. We need to figure out what is our unknown. What is the question asking? Can you tell me that? Well, hopefully you realize that the question is, how many books are we reading each week? Notice that I put B for books. You can use any letter you want. I try to pick letters that have meaning, B for books. Some students just always use X. It really doesn't make a big difference as long as before you start the problem, you define it for whoever's reading your work. That's the first step. The second thing is to identify the pattern. There is a pattern somewhere in here. They may have said it explicitly, word for word, that all you do is translate, or it could be an implied pattern. Let's see what we know here. We're trying to read 450 books. That's the total I expect to read when I'm finished. It says we've already done this, and we have this much time left. How many books do we need to reach our goal? Well, let me think. If I'm reading 30 for 35 weeks, I'm going to be reading a certain number each week. This is counting how many weeks I'm going to be reading. So if I know how many books I read each week, I know that's going to be multiplied by 35 to give me the total number of books I'm reading. So I've got my rate, how fast I'm reading, multiplied by how much time I have. I'm doing B books for 35 weeks, or B books every week for 35 weeks. But this problem's different from the previous problem. Do you know why? Well, it says I've already read 200. That's some work that I've already done. So when I want to find my total amount of work, I'm going to take how fast I'm working times how much time I have, and then I'm going to add on what I've already done, and that will give me my total. Let's see if we can make it fit this problem. In this case, what's my rate? What am I doing repeatedly? Well, I'm reading books every week. Now, since I'm doing it every week, I need to know how many weeks I have, how many books I've already read, and that's going to give me the total amount that I have read. Let's fill in some numbers. How many books do we need to read each week? Well, that's what we were asked to find out, so we don't know that. Times, how many weeks do we have? Well, the problem says I have 35 weeks. But I also have read 200 already, and I know I want to end up with 450 books. There's your equation. Now, I did go ahead and just write this as 35b because we usually don't write the time sign. This is a two-step equation you should be able to solve. Again, I'm going to rush through this because it's not the focus of our lesson, and this should be the easy part for you now. To get rid of the times 35b, or the times 35, we're going to divide both sides by 35, and you get b equals 7.14 books per week. I need to read, or we need to read, about 7.14 books every week in order for us to be done in time. In fact, if I wanted to check and see if I'd make it in time, I'd just do 7.14 times 35, add the 200 on, and it should be pretty close to 450. I did round this off at the end, so it might be slightly off, 449 or 450.1 or something like that. Got the idea? Again, notice you have that constant rate of growth happening for a certain amount of time, but in this problem, we've also added on some work that's already been done. Getting the hang of it? Again, notice we did do all four steps. We defined the variable first, we wrote the equation, we solved the equation, and then we made sure that we answered the sentence. Again, the pattern written in words is for our notes. I would not expect to see that every single time on my students' paper. If you're feeling pretty confident, you might want to try this one on your own. Pause the video, give that a shot, and then listen as I'm doing it. We're going to do the same type of process. Let's read through this. Online shopping might be convenient, but that is not always a good thing, especially if you're the consumer. This is an interesting sentence for the story. It does set the stage, but there's really nothing mathematically useful in that. When shopping is convenient, customers often spend more than they intend to. Well, there again, that's very interesting, but there's not much that's useful in that. Suppose your debit card gives you access to $400. Oh, that seems important. So my debit card will give me a total of $400 to spend. You can spend $99 to join Amazon and spend about $13 a day. It looks like this might be a restriction that our parents put in place, or maybe it's just our own personal goal. I have no idea. Let's see what we can do with that. We spend 99. That looks like this is going to happen once. And we're going to spend about $13 every day. Notice $13 is happening repeatedly. That means that this is probably going to be multiplication. That takes us to the question. The question is, how long can you expect your money to last? How long? This is what we're asked to find out. How long? So the question is going to give us what variable. Can you do that on your own? Pause the video if you need to. I'm going to put D as the number of days. Remember, how long is asking you about time, and our units are given in days in this problem. Once we've done that, we've defined our variable, we want to write the equation, we're going to look for some kind of a pattern. Here's the pattern that I see. We spend $99 to join Amazon. That's Amazon Prime, if I'm being real specific. And then I spend about $13 per day. I have something I've done once, and I have something that I'm doing repeatedly. Can you write that as a pattern? I'd suggest pausing the video, giving it a shot on your own, and then restarting when you feel like you might be stuck or when you've already got it on your own. Here's what I see. I have a rate and I have a time. I'm spending $13 every day. That's my rate. And the question is asking me how long that's going to be my time. But I've already spent $99 just to join Amazon Prime in the first place. And when I've done that, that will tell me what my total work is. In this case, how much I've spent. If I made it more specific for this problem, I would say how fast I'm spending money times how long I have to spend that money plus the money I've already spent tells me the total amount of money that I spend. Can you replace that with variables and numbers? The rate we're spending is $13 every day. The time that we're spending is the number of days. We don't know that, but we have a variable for it. Plus, we've already spent $99. That equals $400 altogether. And when I make it look a little nicer, it's 13D plus 99 equals 400. Hopefully you were able to do that on your own. Again, this is a very, very common pattern. Something that happens repeatedly combined with something that's already done gives you your total. Can you solve this? Again, I'm going to do this quickly because this is not the focus of our lesson. We use the property of equality to get rid of the 99 and the property of equality to get rid of the 13. Using my calculator, I come up with 23.15 days. In other words, I know I will have enough money for 23 days, but on the 24th day, I will run out of money. Make sure after you've solved the equation, you answer the question that was asked. Now, I do have a couple more of these. Again, I'm going to recommend that during each of these you pause, try and do this on your own, then start the video when you get stuck or when you get finished. I think you'll find that to be the most useful way to do this. Also, keep in mind that there are lots of ways to rearrange this equation. You could have done 13D equals 400 minus 99 if you wanted to. Remember, the property of equality lets us rearrange lots of different ways, but what I'm giving you is just a literal story or a literal retelling of what the story is saying. Sometimes I think that's the easiest way to get these problems down. Also notice, I don't read through it once and then instantly jump to an answer. I read the problem, I look for information, I reread, then I reread, and then I read looking specifically for specific things. Make sure you're doing that. We don't read this like we read a pleasure book. We're reading to gain information. Here's one for you. Chuck Norris enters the field of battle. When he arrives, 34 ninjas surrender on the spot. He then defeats 14 bad guys every minute. In total, 277 threats have been neutralized. How long did the battle take? Again, I'm going to ask you to pause the video, try this on your own. If you get stuck, you can restart the video, maybe in portions, and see if what you're doing matches what I'm doing. Again, the first thing I want to do is make sure I understand what the story says and then define these variables. Chuck Norris enters the field of battle. Now that's really interesting, but it's not mathematically relevant, so I'm going to assume I don't need this for the time being. When he arrives, 34 ninjas surrender on the spot. Now this is interesting. He's not even had to do anything. No time has passed. We instantly have 34 surrenders because, you know, he's Chuck Norris. 34 ninjas surrender on the spot. This is going to happen one time. It says that he then defeats 14 bad guys every minute. This is happening repeatedly. In other words, there's going to be some multiplication in here. We're then told in total, we've been given a total, 277 threats have been neutralized. How long? We're asked to find time. How long did the battle take? So the question gives you your variable. Make sure that when you're defining your variable, you're very specific. So when it asks how long, don't just say it's time, but give us a unit of time. What are they asking us for? Well, hopefully you realize they're asking us for the number of minutes. It's the number of minutes that the battle lasts. Make sure you're specific. Don't just put time, put minutes. When you look for the pattern, can you see what's happening in the story? Hopefully you have. This does fit the same pattern as what we've done before. We've got something that's happening repeatedly as time passes. So the amount of bad guys that get defeated depends on how much time we allow to pass. But we do have some additional work that was already done. We had ninjas that surrendered on the spot. That gives us the total work. Or again, specific to this problem, the rate of conquest times how much time we have to complete the conquest, plus the people that were already defeated, gives us the total amount of work. Can you pause the video and write that as an equation on your own? I hope you've already done that. I'm going to go ahead and hop in. The rate of conquest. I'm looking for my rate. It's 14 bad guys every minute. Times how long does this pattern continue? Well, that's the question. That's what I don't know. So that's my variable. Plus, have we already defeated some bad guys? Well, yeah. We had 34 surrender on the spot, giving us a total of 277 threats that are neutralized. That's your equation, and that's me making it look a little prettier for you. Again, pause the video, try this on your own. I'm assuming you've done that and that the solving is really not our focus for today. So I'm going to do this pretty quickly using the property of equality. Notice that D equals 17.4 minutes. That is called a nasty little typo. We need to make sure that our variable does not change without reason, meaning this ought to be M equals 17.4 minutes. So when we answer the question, we could say that Chuck Norris will stop them in about 17.4 minutes. And of course, that's rounded off. Now, I'm finding as time goes on, fewer and fewer of my students are familiar with Chuck Norris and Chuck Norris jokes. If you don't know much about Chuck Norris, make sure you check it out because it is he's really one amazing, awesome, I don't know, super good guy, hero kind of person from the 80s and 90s. So there's a bunch of memes about those. Something like the dark is afraid of Chuck Norris. I like that one. Chuck Norris makes onions cry because he's so awesome. Death once had a near Chuck Norris experience. That's one of my favorites. Chuck Norris doesn't call the wrong number. You answer the wrong phone. And lastly, Chuck Norris doesn't breathe. He holds air hostage. If you're not familiar with Chuck Norris and Chuck Norris jokes, I do recommend that you look him up and do a little bit of research. If you're feeling pretty good, once again, go ahead and give this one a try. This one's called Walk the Dog. Let me read it for you. 3 times a week, you take your dog for a short walk. And 4 times a week, you take her for a long walk. The long walk is 2 miles longer than the short walk. If you walk a total of 29 miles this week, how long are the walks? Have you noticed this one's a little tougher? Again, just because it's difficult doesn't mean that you should stop and just watch me do it. You might want to try this on your own. Give it your best effort. Think through all the things we've already done. And then when you're ready, you can go ahead and continue watching the video. What's the question here? What's the question here? If you walk a total of 29 miles, notice we're given a total. That's important. How long are the walks? How long are the walks? You see, we're asked about the time it takes to do the walks. But what makes this different than the previous problems? Do you know? Well, notice when we talk about the walks, we actually have 2 different types of walks. We have short walks and we have long walks. Very important for us to realize that short walks and long walks are not going to take the same amount of time. And so we have to accommodate that. Here's what I'm going to do. I'm going to make D the length of the short walk. D the length of the short walk. Now, it could be any letter we want. I probably picked D for dog, although S might have worked as well for short walk, or just W for walk. In general, I tend to avoid S's because my handwriting is bad and my S's look like 5s. That's also why I have a tendency to type these videos, type these slides instead of handwrite them, in case you're interested in that. Here's my question though. If D is the length of the short walk, how long is a long walk? Now, I have a couple options here. I could make a long walk a different letter. I could say D is a short walk and E is a long walk. Or I could say X is a long walk or something like that. But we said in a previous lesson that each time I add a new letter or a new variable, I make the problem harder. What's going to be better for me is if I can describe the long walk in terms of d. Do we see anything that compares my long walk and my short walk? Do you see this sentence right here? The long walk is 2 miles longer than the short walk. The long walk is 2 miles longer than the short walk. So let me ask you this. If a short walk is d and a long walk is 2 miles longer than that, how would you describe a long walk? Well, hopefully you realize that it's going to be d plus 2, how long the long walk is. Now, in this case, we're talking about lengths in terms of distances. I believe it's being measured in miles this time. Yeah, we're measuring our length in miles. We're not doing lengths of time. I may have misspoken that earlier. I'll have to go back and watch the video, see if I said that wrong. But our length is being measured in miles. Let's see if there's anything else we can find out. 3 times every week. Oh, that's interesting. 3 times a week. Here's something that's happening repeatedly. That's going to be multiplication. That's a rate right there. You take your dog for a short walk, and 4 times a week, ooh, another rate. 4 times a week, you take her for a long walk. The long walk is 2 miles longer than the short walk. We already dealt with that. If you walk a total of 29 miles this week, how long are the walks? 3 times every week. This short walk is happening repeatedly. So when I do my pattern, I'm going to have that short walk happening repeatedly. It's going to happen 3 times every week. My long walk is also happening repeatedly. Notice this rate times time pattern is happening over and over again. But if I take my short walks and combine them with my long walks, it's going to give me my total amount of work done. So short walk length times the number of walks. Notice that my time this time is not days or weeks, but it's how often I repeat the behavior, plus the length of the long walk times how many times I do it, gives me my total. Can you do this with letters and variables? If so, pause the video, give it a shot. If not, just go ahead and follow along. A short walk length, well, I don't know that, but I know I'm representing it with the letter D. How many of those do I do? Well, this is 3 times every week. What's the length of a long walk? Well, I don't know that. But I do know that the long walk happens 4 times a week for a total distance of 29 miles. Let me clean that up a little bit. It looks like this. 3 times D becomes 3D. D plus 2 times 4 becomes 4 times D plus 2, or D plus 2 times 4 equals 29. Notice that this whole thing is the length of the walk, and so this is my number of times. 4 times the 4 gets multiplied by the entire group. And then I'm going to use my distributive property to pass out the 4. Combine my like terms, that's also a form of the distributive property, and now it's a 2-step equation, which you ought to be able to solve fairly easily. Notice that D is 3 miles. That tells me my short walk has a length of 3 miles. But notice my long walk is D plus 2, which is 3 plus 2, or 5 miles. And that is the answer to the question. Now, these are a little bit more challenging because you've got multiple rates and times, but the principle is the same. For each rate you have, it happens repeatedly for a certain number of times. Sometimes it's hours, sometimes it's days, sometimes it's weeks, sometimes it's a repeated event, in this case, walks. But no matter what, if it happens repeatedly, it's going to be multiplication. Notice since I've got 2 of them, I just combine those. I've got one last problem I want you to give a shot at. Try this on your own. Pause the video and then let's see what we can come up with. Okay, let me know when you're ready. A logging company is planning to make a reforestation plan. So a logging company is making a reforestation plan. That's interesting. Mathematically, it's irrelevant. The company has logged 60 square miles. This is something that's already done. It's been done. It's not going to happen repeatedly. And it is logging, ooh, this is interesting, 10 square miles every year. 10 square miles every year. This is a rate. This is happening repeatedly. If 16 square miles of tree are being planted each year, oh, another rate. 16 square miles of trees are being planted every year. When will all the logged land be reforested? Here's what I want you to do. Start off with defining your variable. What does the question ask you? When will all the logged land be reforested? When is asking me about time. How is time being measured in this problem? Did you say years? Yeah, we need years until the forest is replanted. Let's think about the pattern. On the one hand, the company is still logging land. There's some land that's already logged, and then there's this repeated logging. That's a pattern right there. My work is going to be the work that's already done combined with the work that I'm repeatedly doing. But notice there's a different work that's happening. The work of planting is being counteracted by the work of cutting down. Did I say that backwards? The work of cutting down trees is being counteracted by the work of planting trees. The question I'm asked is, when is the number I cut down the same as the number I plant? Well, let's look at those two separately. The work 1 is cutting, work 2 is planting. My work 1 is a rate, a time, and a previous work. Do you see that in here? The logging or cutting, I've already cut 60. I'm cutting 10 every year. The planting is 16 every year. There is no previous work, so it's just a rate times time. Let's make it relevant to this problem. The rate of logging times the number of years that I log, plus anything that's already done, needs to be the same as how fast I'm planting times how much time has passed. Can you write that algebraically? I'm going to do that now. I'm logging 10 square miles every year, but I don't know how long I have. That's the question that's being asked. But I have also already logged 60 square miles. That means I need that to be the same as how fast am I planting? 16 every year for the same number of years. Notice that I'm logging and planting every year. Both those things are being done. Let me clean it up a little bit for you because those time signs look like X's. This says 10y plus 60, 10 every year plus the 60 that's already done, is the same as 16 every year. Little algebra here, rearranging property of equality, and you get 10. The forest will be replanted in 10 years. That's all I have today. The purpose here was really to get you used to how these patterns often look. Get used to that rate times time and that rate times time plus previous work pattern. That's going to show up in a lot of different instances. This actually becomes extremely important for us when we begin talking about linear equations or two-variable equations later on as well. So try and get used to that. Get used to thinking through the story before you start thinking about the numbers. A lot of times we find that to be very, very helpful. And lastly, make sure that you get well-defined variables. The better your variable is defined, the more helpful it's going to be when you're trying to write your equation. That's all I have today. I do appreciate you guys taking the time to watch. If you struggle with this, you might want to watch through one or two of the examples again. But certainly make sure you come back and check us out again here at Nunley Math. Wish you all the very best. Take care of yourselves. Bye-bye.